In this video, we are going to prove that the complex numbers form a field. Now, we have to remind ourselves, what are the complex numbers? Well, the complex numbers, Z is in C, implies that Z equals A plus BI, where A and B are real numbers. That is the form of our complex numbers that we have. And we have two operators, two ways to add complex numbers. We have addition and we have multiplication. Okay. Now, I'm going to label the addition without the box. And I'm just going to do addition and multiplication. But you can also do it with the box. Now, how do we add how does addition work? Well, addition takes two complex numbers and gives a complex number. And multiplication takes two complex numbers and gives a complex number. That's what we're told in the field. But when we defined our complex numbers, we never justified this. We just said that Z1 plus Z2 equaled A plus BI plus C plus DI was defined to be equal to A plus C plus B plus DI. And similarly, Z1 times Z2, which equals A plus BI times C plus DI, was defined to be equal to AB minus, or AD, or AC minus BD plus AC, or AD plus BCI. And we're just given these two operations, and we have to prove all of these axioms. But we also have to prove this statement here. And these two statements are our closure statements. In fact, we can break these or group these into three main groups. We've got our closure statements. We've got our existence statements. And then we've got our left side equals right side statements. And why do I group them in this way? Well, the reason why is because these names kind of give an understanding for how the proofs behind these works. In these closure statements, what we want to show is that we want to show for any two complex numbers, when you apply addition, you get a complex number. And for any two complex numbers, when you apply multiplication, you get complex numbers. And if for all inputs, the output stays within the set, that is what we call closure. We say the set is closed. Okay. Then we have our existence sets, which is just showing something exists. Okay. So A3 is the zero identity exists. There is a zero complex number. And the multiplicative identity exists. There is a 1 in the complex numbers. And the inverse exists, meaning give me a number, I can give you its inverse. We're showing it exists. Whereas finally, we have left side equals right side. Why do we say left side equals right side? It's because of how these statements are phrased. Okay? In these statements, we say for all A, B, C in F, so we're given three numbers in our field, we show that A times B plus C equals A times B plus A times C. And if we notice here, given generic elements, either of our field or field and vector space when we're proving vector space, the axioms of vector spaces, we define them, we declare them, then we simply show that the left side of our argument equals our right side of the argument. And we go from here across to here using the definition of our operators. So to review, closure, we show that the output of two generic numbers is still within the field. For existence, we make a claim and show it is true. And finally, for our left side equals right side, we declare the variables as general variables and show that the left side of the equal sign does in fact equal the right side. Now you might be looking at associative and commutative saying, well, why are those left side equals right side? Well, recall that associative is that for A, B, and C, this is associative, A, B, and C, and F, A plus B plus C equals A plus B all plus C. And you see that it is a left side equals right side. And commutative, we have that A plus B equals B plus A. So now that we've broken it up into these three pieces, this left side equals right side, existence, and closure, what I'm going to do is I'm going to prove one of each for the complex numbers. I'll prove that addition, that multiplication is closed. I'll prove the existence of the zero vector and the existence of the multiplicative inverse, or the additive inverse, sorry. And I'll prove that multiplication distributes over addition. What I'm going to leave for you guys to work on as an exercise for yourself is to go through the remaining axioms. Determine which type of proof am I doing? Is it a closure proof? Is it a left side equals right side proof? Or is it an existence proof? And go through and see if you can prove it for yourself. Remember, on your quiz next week, you will be asked to prove either that the complex numbers satisfy a collection of these axioms, or one of these axioms, or closure, or you'll be given one of the vector spaces that we've looked at thus far in class and prove that it satisfies either the closure properties or one of the axioms. We start by proving our closure properties. So using our definitions for our addition, so recall these are the definitions. Using the definition of addition and multiplication, we want to show that given two complex numbers, or that for all x, y in C, x plus y is in C. That's what statement 1 says. And for statement 2, for all x, y in C, x times y is in C. I want to show that when we multiply the complex numbers, we get another complex number. Now, how are we going to do this? The way that we're going to do this is we're going to assume closure for real arithmetic, except dividing by 0. So for real arithmetic, as long as we're not dividing by 0, if we combine real numbers, we get another real number. That's our assumption. We're not taking any square roots. It's just plus, minus, add, or multiply, divide by non-zero. We assume that those output a real number. And using that assumption, we're able to prove our two statements. Now we're going to prove statement 1 together. We want to prove that for all x, y in C, x plus y is in C. So if we want to prove for all, we could either prove for everything all at once, or we could consider generic elements. And if it's true for any two generic elements, x and y, then it's true for every element. So we're going to let Z1 and Z2 be in, or instead of Z1 and Z2, because I made the statement in terms of X1 and X2. Oh, it's not auto erasing. We're going to let X, Y be in C. Then be complex numbers. Then what I like to do next is just to tell everyone what that means. What does it mean for X and Y to be in C? I find that before jumping into the meat of the argument, just telling everybody what it means helps get you started. So X and Y are in C, then X equals A plus BI, and Y equals C plus DI, where A, B, C, and D are all real numbers. And at this point, I like to think about what I want to show. What do I want to show? And I'll just do kind of like this box off to the side, reminding myself, what do I want to show? I want to show X plus Y is in C. Well, that means whatever X plus Y is, it's a complex number. So this means I want to show that X plus Y equals, and we'll call it E plus Fi, where E and F are real numbers. So I'm trying to get that whatever the output of X plus Y is, it's some real number plus another real number times I. So that's what I want to get to. Whatever the end is, it's a number plus a number times I. So now that I know what I'm looking for, and I know what I have, we're going to consider X plus Y. Well, X plus Y equals first thing I'm going to do is incorporate its definition. It's just a plus bi plus c plus di by definition of x and y. That's how we defined it up here. It's just a generic value. But now that I've done this, I'm able to add. I have my definition of addition. So this equals a plus c all plus b plus d times I. At this point, it might not seem clear how to move forward, but if we look at what we want to show, we want a single real number plus a single real number times I. Now, we said we were going to assume closure, which means any combination of real numbers is another real number. As real arithmetic is closed, a plus c is in R, and b plus d is in R. Well, what does this mean? This means I have a real number, whatever a plus b is, it's a real number, or a plus c is, it's a real number, and I have a plus another real number times I. Well, thus, x plus y is in the complex numbers, because x plus y is equal to a real number plus a real number times I. Now, if this isn't quite clear enough for you, a nicer statement might be as a plus c and b plus d are real numbers, and x plus y equals a plus c plus b plus d I, x plus y is in the complex numbers. And this is our proof for closure. We have shown that given any two complex numbers, when you add them, you get another complex number. See if you can take some time and prove the closure of multiplication. Given any two complex numbers, when you multiply them, prove that they form a number of the form real number plus real number times I. We are now going to look at our existence proofs. Now, for the existence proofs, I like to say this is like getting pizza or showing me pizza. I would like you to show me a pizza. The first step is bring the pizza box over, or make a claim. And the second step is open the box, or show the claim works / is true. So for these proofs, you are making a claim. You are saying, consider this object. Okay. And then you say, look, it acts like the blank. So when I'm saying there exists an additive identity, I'm just going to tell you, hey, here is the object. That's step one. You define it, you say, look at it. This is the object. Then step two is you prove that it's correct. So for this existence, we have four existents. The four things that exist are the additive identity, the additive inverse, the multiplicative identity, and the multiplicative inverse. We have four things, okay? And we've got to prove that each of these exist. Again, we're allowed to tell the world what it is. In fact, we want you to tell the world what it is. We want you to make that claim. Consider this object. Then show me it's correct. So here, we have defined in class all four of these. All four of these have been given in the notes. Okay, so you can go and you can find them, but then you should go through the exercise saying, hey, consider this object and prove that it satisfies being the additive identity, additive inverse, multiplicative identity, and multiplicative inverse, using the definition of addition and multiplication. What I'm going to do is I'm going to show you the existence of the multiplicative identity. Okay, so we're going to prove this one together. consider 1 plus 0i. Note 1 plus 0i is in the set of complex numbers, as 1 and 0 are real numbers. Let z be another generic complex number. Then, well, what does this mean? This means that z equals a plus bi, where a and b are in the set of real numbers. Now, at this point, when we start defining all our things and we're getting in, it's really common to lose yourself in what you're supposed to be doing. You just define your objects and you go, oh, what am I supposed to do? So what I like to do at this point, before I jump into the proof, is again, write a little box off to the side of what I want to show. Just so that I can remember, okay, what am I trying to show? What we're trying to show is we're trying to show that 1 plus 0i times z equals z, because that's the multiplicative identity. And that's what that would imply, that 1 plus 0i, this is my 1 for my field. So that's what I want to show. So what should I consider? I should consider this left side. So I'm going to consider z, or 1 plus 0i times z. And my goal is to show that it equals z. So 1 plus 0i times z equals 1 plus 0i times a plus bi by definition of z. Now, at this point, it's really tempting to expand and just FOIL. But remember, we have to use the definition of multiplication here. So we have to jump to this form. We have to. And here, this is my A, this is my B, this is my C, this is my D, because that's where they show up in this expression. Okay. So what comes first? Well, I have A times C, which is 1 times A plus, or minus, sorry, minus B times D. And B times D is 0 times, in this case, B, plus, and now I'm going to do A times D, which is 1 times B plus 0 times A, I. And this is by definition of complex multiplication. And now what we can do is we can do our real arithmetic. In this class, we're allowed to do our real arithmetic. So this equals A plus B times I by real arithmetic, which is equal to Z by definition of Z. And we have our proof. Now, ending the proof there, some of you might look at that and go, yeah, that makes sense. Or some of you might look at that and go, oh, why does that end? So it's always nice, if there's a little bit of hesitancy, to add a final statement. I like to say that if in doubt, write it out. As 1 plus 0i acts like the multiplicative identity for a generic complex number, it is the multiplicative identity. And what this means is, thus one exists. And technically we shouldn't say the, we should say a, but shortly we'll prove that for fields and for vector spaces, the multiplicative and additive identities and inverses are unique. But that's to come later. Last but not least, we have our left side equals right side proof. Remember, we call these left side equals right side proofs because we're proving that the left side of an equation is equal to the right side of an equation for generic inputs. Okay. So this includes A1, A2, A5, A6, and A8. And a significant number of the vector space axioms are also left side equals right side statements. We are going to focus on A8. I'm going to leave A1, 2, 5, and 6 for you guys to work through. So what does A8 state? It says that for all A, B, C, and F, A times B plus C equals A times B plus A times C. Now, here it has the box plus and multiplication. But in our original definition, we don't use the box plus multiplication. So in the proof for this statement, what we would do is we would drop these boxes because our operators don't have boxes on them. The first operator we defined is still multiplication, and the second operator that we defined is still addition. Okay? Now, how do I prove this? Well, to prove it, we need to consider, or we can simply consider 3 generic elements and prove that it's true. And if it's true for any 3 generic, it's true for all. So we start by saying let A, B, C, B, and F, or in our complex numbers. But this A, B, and C, we don't really like that for complex numbers. For complex numbers, we prefer to use Z's. Just that's our preference or convention. So we're going to label it Z1, Z2, and Z3. And if you want to put a little tick across, you can. If you don't have to. Okay. Now, if I'm going to let 3 values be complex numbers, let me tell you what those 3 values are, or let me define them, if I can, more specifically. So that then Z1 equals A plus BI, Z2, and I'm going to label A1 plus B1I. Z2 is A2 plus B2I, and Z3 equals A3 plus B3 times I. Okay. So I have my complex numbers, and I want to show that left side equals right side. So I want to somehow go from the left side to the right side. And again, we ask the question, how? And with complex numbers, we are going to steal from it being true for the real numbers. So we're going to assume that this property, this distributive property, is true for the real numbers. And we want to somehow utilize that to prove that it's true for the complex numbers. So what am I going to do? I'm just going to start with the left side. I'm just going to consider. And what I like to do is I like to consider with the most compressed side. So this A times B plus C, to me, that's the most compressed side. And I want to expand as much as possible. I want to distribute. So here, this A plus BI, remember for our case, our variables aren't A, B, and C. They are Z1, Z2 plus Z3. First thing I'm going to do is I'm just going to introduce our, not necessarily nicer definitions, but definitions we might be able to work with a little bit more. So this is A1 plus B1I times A2 plus B2I plus A3 plus B3I. And this is by definition of Z1, Z2, and Z3. Well, now this big bracket's not nice. So if I simplify this using addition, I can do a multiplication later. So I'm going to use the definition of addition of complex numbers here to give me A1 plus B1I times A2 plus A3 plus B2 plus B3I. Well, now I have 2 complex numbers that are multiplied by each other. So this was by the definition of addition. Here, I now am going to multiply them. And I've got to remember that it's AC minus BD. So it's A1 times A2 plus A3 minus B1 times B2 plus B3, all plus, I'm going to give myself a little bit more space here, A1 B2 A2 plus B3 plus B1 A2 plus A3, all times I. And looking here, I don't really know where to go from here. I'm kind of stuck, okay? So while a formal proof, a well-written proof, we like going all the way from the left to the right, what I'm going to do is I'm going to say, let's say that this is equal to my left side. And now my right side equals, and I'm just going to go back to the right side. I'm going to say, what's going on there? What does that start with? Can I simplify that down and somehow work toward equality coming from the left and from the right? Because I'm not sure exactly how to move forward. And that's fine. We can do that. So Z1 times Z2 plus Z1 times Z3 equals A1 plus B1 I times A2 plus B2 I plus, and let's fix that, make it a little bit more clear, B2I plus A1 plus B1I times A3 plus B3I, which is equal to A1, A2 minus B1, B2 plus A1, B1 plus A2, B1, or A1, B2 plus A2, B1I plus, now I'm going to look at my next multiplication, which is A1, A3 minus B1, B3 plus A1, B3 plus B, or A3, B1, I. Okay, and I'm still adding two complex numbers, so I'm going to add them together. This line was by definition of Z1, Z2, and Z3. This is by definition of addition. Or sorry, not by definition of addition, by definition of multiplication. And if we go back up, this here is also by definition of multiplication. You'll notice that I forgot some steps. That's okay. When you're going through and trying to prove these, if you can't remember exactly the rule, move on to the next and come back to it. And as you're going through, if you realize, oh, I forgot to justify, don't erase everything. Just go back off to the side, add that justification. Well, now these are two complex numbers added together. We've got to combine them. And now A1, adding them together gives me A1, A2 minus B1, B2 plus A1, A3 minus B1, B3, all plus A1, B2 minus A2, B1 plus A1, B3 plus, oh, there should be a plus here, A3, B1, all times I. And now I'm going to look at what I have on the right side, and I'm going to look what I have on the left side. Here, they look similar, but there's an expansion that needs to happen. So this left side, I can expand because it's true for real numbers. So what I'm going to do now is I'm just going to take a second to expand here. Expanding here gives A1, A2 plus A1, A3 minus B1, B2 minus B1, B3 plus A1, B2 plus A1, B3 plus B1, A2 plus B1, A3 all times I. This is as A8 is true for real numbers. Right? So this is my left side. So I've got my left side worked, I've got my right side worked, and we can see that the left side equals right side. And they're not quite perfect. You'll notice we've got add, subtract, add, subtract, add, subtract, add, add. But they don't appear in the same orders, but they look similar. So to get from here to here, we need to use associativity slash commutativity of real arithmetic. And I'm going to leave this as an exercise. In fact, I'm going to leave the rest of the left side equals right side proofs as an exercise. But the whole point is that using the definitions of additions, as well as assuming things to be true for real numbers, you get from one to the other. Right? This concludes the video on fields. The next video, we're going to be looking at proving some of the axioms for a vector space Fn.